Hello, and welcome back to the web series Developing SPECTER using Innoslate's digital thread. My name is Mallory Jones, and I'm a systems engineer here at Spec Innovations. In the previous videos, I introduced the Break the Ice Challenge, initiated the Lunar Rover project, and demonstrated Task 1, Research and Design. In this sixth video of the web series, I will demonstrate the work conducted during Task 2 of the Lunar Rover project. This task was crucial for building the rover's subsystems and assembling the SPECTER lunar rover prototype. To complete Task 2, build the lunar rover prototype, Innoslate's modeling and simulation and integration tools, SDK, MATLAB, and GitHub were utilized throughout the following processes demonstrated in this web series video. In the Systems Engineering V model, this work took place during the hardware and software acquisition phases. The Task 2 statement of work was broken down into three subtasks: build 3D printer and print additional equipment, assemble the lunar rover prototype, and incorporate Innoslate's digital thread. From this task, a final report was produced, and the SPECTER rover prototype was developed. A Creality Ender 3D printer was purchased for 3D printing the additional materials identified during Task 1 Research and Design. Upon delivery to spec, it was assembled and a print test was conducted to confirm the 3D printer was functioning properly. Additional equipment was then printed for the lunar rover prototype. This included 2 halves of the excavator claw to be attached to the robotic arm for regolith excavation, a complete storage container to store regolith and water during navigation between the various sites at different phases of the mission, 4 tire fenders to cover the lunar rover prototype tires and protect the rover body from dust abrasion or environmental obstacles. Issues were tracked throughout Task 2 to monitor and manage any problems while 3D printing and building equipment. This was done to avoid issues quickly turning into risks if not resolved. In Innoslate, issues were created by going to the database view, selecting new entity, and choosing issue. The issues were provided a name, description, current status, and priority level, and assignee responsible for monitoring the issue. To track the issues, a database query was created to quickly access a list of open or in-progress prototype issues. The database query is used to filter entities in the database view, and once selected, it automatically searches and sorts the database to locate entities that meet the query requirements. Once an issue was resolved and no longer has a probability of turning into a risk, the status attribute was changed to close. Upon delivery to spec, the robotic arm was assembled with its servo motor and Raspberry Pi. The 3D printed excavator claws were then mounted to the robotic arm grabbers to create the excavation subsystem, and the Raspberry Pi was configured to be controlled via a remote. The Leo rover prototype was also assembled upon delivery, and its Raspberry Pi was configured to be controlled via a user interface from a SPEC laptop. Once all the lunar rover prototype components and subsystems were printed, built, and assembled, the final product was Spec Innovations SPECTER, a lunar rover prototype. SPECTER stands for Space Prospect Exploration Convoy, Transporting and Evaluating Regolith. A user interface was then created to control SPECTER. This was done by utilizing a repository provided by the Leo rover prototype. It was then modified in GitHub to add displays and data readings imperative to the lunar rover mission. Leo rover's firmware allows messages to be sent from the user interface to the prototype's equipment and components to command functions to be performed. Vice versa, the user interface also allows data and messages to be displayed to the operator from the Leo firmware. Important features of the user interface included a distance reading of how far from the front and rear of the prototype body obstacles are approaching. These distance values are received from the enhanced LiDAR equipment on the SPECTER rover. An obstacle collision warning is then displayed on the user interface if the rover body approaches an obstacle too closely. The user interface is also used to control the movement of the rover prototype. Clicking and circling around the rover drive control allows the operator to control the prototype directly on the spec laptop. The GitHub repositories will be discussed further in the following web series video. Up next in the web series Developing SPECTER using Innoslate's digital thread is a video demonstrating Innoslate's integrations. Thank you again for being here today, and I'll see you in the next video.